Good morning, everyone, and welcome to the webinar on food waste recovery, driving methane capture and circular economy. As a matter of form, I should point out that this webinar is recorded and will be shared afterwards. So this is today's agenda, where we will have 4 experts working within methane capture, biogas production, and circular economy. After these presentations, we will have a Q&A session, so please feel free to ask questions afterwards. My name is Emil Slevčević, and I am a junior commercial advisor in waste, recycling, and biogas advisory at the Trade Council of Denmark in North America. I would like to thank New York Circular City Week for giving us the opportunity to share knowledge about Danish solutions on turning food waste into a valuable asset in a circular economy. So, who is the Trade Council? The Trade Council of Denmark in North America is a part of the Ministry of Foreign Affairs of Denmark that help Danish companies establish themselves in foreign markets and expand their activities all over the world. In North America, the Trade Council of Denmark has around 80 advisors divided between different sector teams, including the water and environment team. The Waste, Recycling, and Biogas Advisory is a part of this team. This webinar is held in collaboration between the Trade Council of Denmark in North America and Biogas Go Global. Biogas Go Global is a triple helix partnership between the Danish Energy Agency, Food and Biocluster Denmark, that is a cluster organization and innovation hub for the Danish food and bioresource industry, as well as the Waste, Recycling, and Biogas Advisory at Trade Council of Denmark. With Biogas Go Global, we wish to increase knowledge sharing and experiences of biogas, and through that establish partnerships. The companies that we work in that you have the pleasure of meeting today. Our first speaker is Claus Gunge Ellegaard Mortensen, business developer, incubator, and investor relations manager at the Food and Biocluster Denmark and director of Biogas Go Global. Claus has been in the Danish bioenergy industry for 8 years, where he has been involved in biogas sector analysis and facilitating innovation activities between companies and universities. He will provide us with knowledge on how biogas is driving the circular economy in Denmark. Claus, the floor is yours.
Much for the introduction and for the opportunity to present here today and share some of the insights we have from Denmark and the let's say the revolution we've seen since 2013, where the biogas boom in Denmark took off. I'm going to spend the next 14 minutes on elaborating a bit about the role of food waste in the agricultural industry, in the AD industry in Denmark. We could talk a lot about the energy side of biogas and renewable natural gas, but I'll stick a bit more to the food waste side today, and also the role of cities in this. As mentioned before, I'm the director of Biogas Go Global. That's a partnership between the Danish Energy Agency, the Danish Foreign Ministry, and the Food and Biocluster Denmark. We are working in some 5 countries right now with knowledge exchange between policy, industry, and academia. And my contact info is here, and feel free to reach out if there's specific topics that you are interested in learning about from a Danish side. Let's see if I can share here. Here we are. So when we talk about biogas production in Denmark, we need to talk about more than energy. So in Denmark, the reason why also the Danish government been quite supportive throughout the years for biogas and AD is due to the fact that it is a part of it's a silver bullet solution for many of these society issues we see. A bit about the context. Denmark is a small country, 5.6 million people, highly, let's say, a big food producing country with a lot of household livestock production, which causes to some extent agri-environmental issues. So in this context, this is where you should see biogas, basically. even though that Denmark is well known for also wind turbines and wind power and solutions within that, actually 2/3 of our renewable energy share is bioenergy. So besides the production of renewable natural gas, that is also combustion, burning straw, burning wood pellets and wood chips, basically. So we have a fairly large share of renewable energy in Denmark. Biogas plays a role in this. A bit about the policy. Also, we have a tradition in Denmark of working quite a lot together. Also on the policy level, we have 10 parties in the parliament. Many of these, and the majority of these, 8 to 9, are supportive towards both the transition of the agri sector in Denmark, but also the renewable energy acts, which are coming through on policy side. So again, the role of policy is to create a good investment environment for investors that can think long term. That when there's a shift in government, then you don't see also a shift in policy, because you need to be able to think 10, 15, 20 years ahead. So that's a key takeaway, which are not related to technology here. I just want to touch a bit upon the feed over fuel, because that's some of the issues we see in Denmark right now, is that many of especially the food industry and their food waste streams, that there's a competition between the farmers who want this, let's say, spent grain from breweries, want this as feed over, let's say, other fractions which are relevant for biogas production. But from the biogas association side in Denmark, there's a clear line that if a feedstock it's good for feed, we should use it for feed and not for fuel in a biogas plant. So again, I talk about this silver bullet, and again, biogas is much more than just energy, and these are some of the reasons why we from Danish society invest in biogas. Of course, these times with Russia and the gas crisis in Europe, the prices have risen, and we see ever increasing and big demand for solutions within biogas. But if we again turn away from the energy, we have the different aspects of the impact from, for instance, livestock production. There's a lot of arguments why manure should be degassed in a biogas plant. Basically because the manure smells less when it's been through a biogas plant. It's also, let's say, there's a higher availability of nutrients, which means that the fertilizer value of manure is higher once it's been through a biogas plant. So again, think about the circularity in this. Think also in let's say, this symbiosis between cities and rural areas, that rural areas supply the cities with energy, with food, and you see the conversion back from the cities with waste streams that the farming community can handle and use as fertilizer. This way we create the circular economy. I'm not going to go deep into for instance, the CO2 for P2X, but that's some of the stuff we see in Denmark and where the industry is really growing right now. From a technology and process level, throughout the, let's say, 35 years of biogas in Denmark, our experience is that there's a huge economy of scale. So the biogas plants in Denmark are typically, the newer biogas plants are typically plus 200,000, 300,000 tons of input. When that being said, there's really no size fits all. So you need to adapt the plants to the specific biomass available, but you also need to have flexible plants, because again, you never know what kind of waste streams you have from society. What is also a bit unique is the ownership and management of the plants in Denmark. Is that basically the farmers, some of the farmers have an ownership in the plant, which creates this alignment that you can secure the biomass feedstock on a long term, and you also can give back the digestate from the plant and use this in farming. And then again, I think a key takeaway is also that that operation of biogas plant should not be a part-time job run by a farmer. It should be a full-time job for professionals. So I actually wanted to draw the waste value chain from households. I couldn't really find a decent enough, let's say, a Danish graphics of the value chain. So I decided to draw my own here. I'm not a graphic designer, but basically you have, starting from the food in Denmark, we separate in a small green bin that's below almost every household in Denmark's sink. That's where we gather all the leftovers from our plates. Then it goes into one of the sections in one of the bins you see to the right here. We have, the municipalities are responsible, of course, each inhabitant is responsible to do the separation, but it's the municipality operating these waste bin systems, basically. Then once it's outside, then this could also be a solution for more urban areas. The good thing about this is below the ground, so you avoid any rats and other pests that you don't want. But then it's gonna be picked up by a truck run by a private company for a food waste pre-treatment plant, which is the majority of the food waste in Denmark is handled by Methane a solution from them. You will hear from them later. I think what is important here, and I forgot to say that in the separate waste bin, is we had some issues in Denmark concerning choosing the right bag. I think we are not using biodegradable bags anymore. We're using a bag which is anyway separated in the reject in the food waste pre-treatment plant. Then from the food waste pre-treatment plant, you'll get a biopulp, which is again used for biogas production at the AD plant. In Denmark, we have a new gas strategy. I'll come back to that, but basically that is we need to use the gas where we need it most and where the electrification can't happen. So that's in industry where there's a high demand for high temperature. It's also in transport sector and less in homes for heating. What is important when you have the biopulp coming out of the food waste pre-treatment plant is that it's of a high quality, which enables the farmer to use it. In Denmark, we have strict laws on the application of diastase. I'm not going to go into that, but it's basically seen from a Danish farmer point of view that the diastase is a really, really good fertilizer with the same quality as what he buys from Yara and some of the other suppliers, chemical fertilizer. So here you have the loop, then the farmer, of course, produce the food and we can continue the cycle. So again, see food waste as a resource, creating more food again. This is a small calculation I made that we sometime when we talk about food waste and biogas, again, we talk a lot about energy, but the fertilizer that food waste replaces is quite significant, and the big production sites producing ammonia and chemical fertilizer represent a huge global energy consumer. 2% of all global energy is used in this process, the Haber-Bosch, and that calls for around 3% of the total greenhouse gas emissions. So again, we need to think about what we're replacing in a more sustainable way. We also need to think about jobs, because when you create these local and, let's say, regional value chains around biogas, you create quite significant number of jobs. And that's jobs in parts of countries in the country in rural side where every job counts. So again, this is a picture of the Nature Energy core school plant. The story behind this plant is actually it uses the, of course, you create biogas. When you create biogas, you clean the biogas for CO2. That CO2 is actually used in food, in the food industry. So again, that's a side stream. That's a product out of a biogas plant, which again can be used in the food industry. But when we talk about biogas, do remember to think about the jobs and the local economy it creates. This is taken from the new green gas strategy that is developed by the Danish Energy Agency. And I think, again, I'm not going to read it out loud, but there's 9 points here which should be, we should think about when talking about producing and using gas. So that's on the gas consumption, that's the production, and that's the infrastructure. So again, we need to use the gas because it's in the right places at the right time, because gas is storable. We can easily put it into the ground, which electricity can't. Furthermore, is that the green gas must be produced sustainable, which means that we need to decrease the leaching of methane from the biogas plants. We need to use sustainable feedstocks. We are not using very much energy crops. I think it's less than 4% of the input is energy crops, which again, I will emphasize that the biogas plant needs to be a place where we handle waste and not food. Food and Biogas Denmark is also working with partners in Europe on upgrading these types of fractions from biogas plants. And this is one of the projects we participate in is valuable waste, is for instance to use methane to produce food, a protein source. Of course, also you can use the digestate for insects, which also can be used for protein. And then again, the last part is making it circular economy, bringing the nitrogen and phosphorus back to the soil. We have gathered, I'm lucky to work with good people in the Danish Energy Agency and the Foreign Ministry and Trade Council in North America. And we put together a few reports on some of the most important stuff and elements that has created the Danish biogas sector. To the right, it's a report showing the experience, the insights and experience from the Danish biogas sector in the middle of the green gas strategy. And to the left is basically an overview of the plus 50 reports that basically build the policy around biogas in Denmark. So that's available for download at biogasgoglobal.com. And then, last but not least, I hope to see some of you at either Value for Biogas East in Toronto or Biogas Americas in Las Vegas. Thank you for your attention.
Thank you very much. Now we will have our next expert, that is the CEO of the Danish company Renew Energy, Morten Gyllenborg, who will present and so that we can gain some more knowledge on the industrial scale renewable natural gas production and nutrient recovery. Morten has almost 2 decades of experience from the energy industry, of which the last half has been within development and optimization of bioenergy projects. Morten has also been working for Renew Energy for about 1 year, and he is now in charge of expanding Renew's portfolio of bioenergy projects. Morten, the floor is yours. Thank you.
Thank you very much, Damien. Thank you for this introduction. I will, due to that, simply just jump into the presentation, and hopefully it should be working. Thanks for the opportunity to speak here. I'm Morten, representing an energy company, a bioenergy company that's been working in this space for roughly 30 years. We have our main offices in the southern part of Denmark. We serve Europe out of that, and then we have a local representation in the United States as well as in South Korea. We have a project design reference portfolio of roughly of more than 300 projects, and we also hold a patent in the US on nutrient separation. Basically, what we do is we design facilities, typically industrial scale. Excuse me. And when we talk industrial scale, for us, it doesn't have to be necessarily thousands of tons, because it depends a lot upon the feedstock, and I'll get back to that in the next couple of minutes. But typically what we see is, if we're talking food waste, a couple of hundred tons and upwards. I believe the largest project in our current portfolio is 5,000 tons of food waste per day. So up to relatively large facilities. We have a design philosophy, which I think we share across a lot of other Danish companies and companies from Europe, is that we work a lot with process integration, robustness, such that, as Claus also mentioned, flexibility is a core, durability is a core. And then one thing that is very, very important is the optimized energy consumption, or in another word, OPEX. When it comes to energy facilities, I think one important takeaway for many facilities is that CapEx is actually not very important, except on day one. The next 20 or 30 or 40 years of a facility's life, it's all about the OPEX. And then we're a lot about the automation control, optimizing the facilities to the extent possible, optimizing where it makes sense, and bringing all of that together in a sound, stable, and robust facility. Just to recap on the circularity that Claus also mentioned before, what we're working in is basically a circular economy, and I think I took the liberty of saying the circular economy driver, anaerobic digestion, because it's at the core of, and it's in my opinion, at least probably the best example of circular economy. Also, a few words on food waste. Food waste itself is an overlooked resource. It's in its very nature a shame that so much food is wasted along the way. But it is both abundant and it is available in every industrialized country across the globe. It's estimated by UN that up to a third of all food is lost somewhere along the value chain, and we need and should and can make good business of picking this up and utilizing it. There's a lot of aids, again, also as mentioned by Claus, transforming waste handling, avoiding landfilling, making soil improvements, and recirculating nutrients. And those two things are actually not the same, because when you're talking chemical fertilizer, what you often lack is the carbon, which is recirculated using the biogas or digested. But of course, in any case, it will crowd out chemical fertilizers. There's a security of supply issue, local production of methane, biomethane, which up until very recently was not at the focal point of very many, but due to the recent events and crisis and war in Europe, of course, this has come to light as a key driver. When we are talking anaerobic digestion, we typically see facilities that are made up of different types of feedstock. Food waste is one of them, but I would typically put them into three different categories. Talk about high yield products with potentially very high yields. This could be different kinds of oils and glycerines, etc. And those would come with some different characteristics in terms of how long you can contract them, how volatile the price is, but also with a limit as to how much you can use them. Then there is the medium yield products, which would be, for instance, food wastes, industrial waste streams, etc. But also some specific types from farm waste that could be used. And then there are the low yield products, which are animal wastes, slurries and manures, which are probably the ones that have been targeted the most in US, at least because of the specific schemes around the low carbon fuel standards. I've taken the liberty of trying to rate them into different types. I'm not gonna go into a lot of detail about it, but what I'm trying to say here is basically that we should be aware that by not targeting more than we do already the food waste segment, we are bypassing some relatively valuable value streams in the biomethane industry. You have a lot of food waste out there and it's ready to be used. You can be guaranteed supplies for a long time. The prices are not too bad, and the price volatility is not too high either. Whereas with some of the farm-based products, you will have considerably lower yields per ton. So anaerobic digestion, basically at its core is I put it here like Mother Nature does it. There's no magic to it whatsoever. It's basically 4 different chemical, biological processes that goes on within the digesters, producing the biogas consisting mostly of CO2 and methane. And what we need to realize here is that actually, when you look at it from a more holistic perspective, when you look at the biomass that comes in and whatever comes out and pays for the whole thing, when we look at it traditionally and look only at the gas or the energy that comes out of the gas, we're talking a revenue stream that is based on less than 5% or around 5% of what comes into the facility. And I think based on also Klaus's focus on the nutrients, I think it's very important that we try to readdress this and realize that there is a lot of value to be picked up in the biosolids and the digested itself. Historically, many facilities have been producing heat and power, which of course is a more local use. You have to get a viable business case, get some sort of value out of the heat. At least in Denmark, that is an issue in the summer, and that's one of the reasons behind us targeting RNG more here. And now there's I'd say about 70 to 80% of all biogas produced here is now purified and injected in the grid. Can be used as any other gas, basically as natural gas. As a company, we are relatively technology neutral, but we're not neutral in terms of how we best integrate them. And this is a little back to the optimization of the value streams and the reduction of internal cannibalization of the energy. So we do tend to include amine scrubbing in the facilities in order to produce a high quality RNG and have a very, very low leaching of methane. And basically, the leaching is a core element in choosing the correct sort of absorber and stripper in these solutions. When we have an AD facility, there would be many value streams to choose from. You would have on the food waste side, you would have some tipping fees to work with. Then depending on how you choose to run your facility, if you are doing RNG and you choose an upgrading equipment that provides you with a pure CO2 stream, then you would have the RNG itself, you would have the CO2 to work with. You would have on the digested side, solid fertilizer. You could have biochar if you choose to pyrolyze the fibers. You can work with ammonium sulfate. And you can then have another one that is often overlooked as well, is the processed water. I mean, water is also a resource that is becoming more and more scarce, and we can also recirculate that in the facilities. So as a recap of what I've just been through, there is a large potential of producing RNG from food waste or similar waste streams, both in the US and elsewhere. The RNG and the nutrient recovery systems are and becoming higher and higher value drivers across the globe, as well as in the US, based on both increasing energy and food scarcity, and of course the GHG reduction targets. We have in Denmark and Scandinavia off-the-shelf solution. You're going to hear from some of them in a minute, especially Gimmidan is coming online. And we have introduced and used these solutions successfully for many years, and it can easily be replicated in the North American market as of tomorrow, later today if you hurry. Thank you for your attention. You're welcome to reach out. There are some extra slides that you are welcome to look at also, but due to the time, I will stop it here. Thank you very much.
Thank you, Morten. Thank you very much. Now I would like to introduce, as Morten also said, that CEO Lars Ravn-Nielsen of Gimmidan EKG will present how to extract the maximum energy and nutrient benefits from organic waste sources in the most efficient way. And see that Lars is ready. Lars is responsible for the overall business activities, including the worldwide sales activities of Gimmidan EKG, and he has more than 30 years of experience working with international business and has since 2016 been working with pre-treatment of organic waste at Gimmidan EKG. Lars, please go ahead.
Thank you very much, Emin, and I will thank everybody that I get the opportunity to tell you a little about our pre-treatment solution. Our philosophy is that we want to provide a system to extract the maximum energy and nutrient benefits from different organic waste sources. And the basic tenets of our systems are: 1, flexibility to accept any type of packaging. That means plastic, glass, paper, or metal. And we want to produce a clean, quality biopulp that will maximize the gas production and provide a high-value fertilizer. And our system has low maintenance and labor requirement. Here you can see a drawing of a standard EKG facility. And this system is not just a depackaging system, it's a fully integrated solution for food waste pre-treatment and biopulp production. And if you look in the right-hand side, you can see the feed hopper where you put in the waste, and you can put in the waste either with a front-end loader or an automatic crane. And then it goes with a screw conveyor up to the pulper, where we add water to the waste and then rotate the waste. And during that pulping process, the packaging will be opened so we get access to the food waste inside. And then the food waste will be dissolved in the water. When the pulping process has ended, and that means after approximately 10 minutes, there is a valve in the bottom of the pulper that opens, and then the whole batch will go down in the separator where we separate the organics, that means the fluid part, from the inorganics. And the inorganics we then wash twice to get all the oil and fat that's sticking on the plastic, for instance. And when that has ended, there's also a valve in the bottom of the separator, and then it goes to the reject, goes down to also to a screw conveyor and goes to a screw press where we press all the fluids out of the reject. And then you can recycle the reject afterwards. And all the water we recover here, we will use in the next batch. So we have no outlet from the system, except for the biopulp that is the product of the process. And if we look at the system, we have a capacity on between 10 and 13 ton of waste per hour. And that means approximately 250 ton a day if you run 24 hours. And if you have a higher demand, you can put in additional lines. The dry matter content in the biopulp is adjustable between 10 and 18%. Due to the process, we have a very small particle size in the biopulp, and that allows for an accelerated biogas production. And we have a highly automated system with low OPEX, and the scatter system can be operated remotely, and the staffing is approximately 1 to 3 hours per day or per shift, and that depends on the configuration. And the flexibility of the system is very high because it's a combined depackaging and pre-treatment system. And during the pulping process, the packaging will be opened and allow the organics to be dissolved into the liquid fraction. And here we have what we call a low impact approach. That means that we treat all the inorganics as soft as possible so it stays in bigger pieces, and then it's more easy to remove afterwards. And that means that the system is able to treat, probably manage food waste from residential, commercial, institutional, and industrial streams. And here you can see some example of packaged foods. In the left-hand side, you can see some, I think it's teas in some metal cans, and also some beers in bottles. I will, by the end of my presentation, show you a video from one of our sites, and there you can see how we treat the waste. And of course, we also can treat more normal type of waste, as you see in the pictures, and we can also handle waste with some contamination, and up to 20% contamination, we have full capacity in the system. And the pureness of the biopulp is very important if you want to use the end product from the digester as a fertilizer. And as Klaus explained before, it's very important for the farmers to get a good fertilizer, and that was basically how it's all started. And the pureness of our biopulp is second to none. And our system is the only food waste pre-treatment system to obtain an ETV certificate. And ETV means Environmental Technology Verification, where a global third-party verification program for environmental technologies. And that documents the efficiency of the system. If we look here, that's apart from this ETV certificate, and the whole certificate is a report on 50 pages. But here you can see in the first line where they have checked the purity of the pulp for all impurities. And you could see we have 99.96 is organic. And if you only check for plastic, it's even higher because plastic has a very low weight. And we expect in the future that we will get even more strict regulation for use of the digestat as a fertilizer. And that will demand a higher purity of the biopulp. And in Denmark, we don't only measure the weight of the plastic, we also have to measure the covered area of the plastic. And all these future demands we are prepared for by Ecobee. We also make analysis of our pulp every month. and we make a declaration. And here you can see a part of one declaration. And if you could see in the first line, you can see we measure the area of the plastic, and in the second line we have how much plastic we have in the dry matter, and you can see the results is 0.006. So that's nothing. And if you look at the total physical impurities, you only have 0.43%. So that's a very clean pulp. And we, of course, also check for a lot of other things. And you can see in the third column, we have the legal value in Denmark. And then in the fourth column, we have our own limits, because we want to ensure that our pulp can be used as a fertilizer by organic farming as well. And therefore, we use lower value as a limit. But as you see in the next column, we are far below this low limit. So a lot of our pulp is ending up by organic farmers. And as Claus mentioned, there is a high value of the gas potential in the pulp. Claus mentioned a value on approximately 500 cubic meter of methane per ton of organic matter. And you can see in this sample, we have 544 cubic meter of methane. And you can also see that the dry matter in the pulp, 89.1% of that is organic material. And here you can see an example of one of our plants in Denmark. That's on an existing waste to energy facility where they have taken out one of the incinerators and installed one of our lines. And in the yellow square, you can see the building where they receive the waste. And in the round yellow circle, you can see the tank where they store the biopulp, and then it will be transported with a truck to an AD facility. Here you can see a greenfield product from the north of Denmark. And from this facility, I'll show you a video by the end of the presentation. And here you can see in the right-hand side, we have a lagoon where we collect surface water from the area. And this water is being we use during the process. And here you can see the newest plant in Denmark. It's a plant with 2 lines near Copenhagen, where this facility treats all the food waste from the Copenhagen area. And this facility will treat more than 100,000 tons a year. And now I'll show you the video from the facility in Frederikshavn in the northern part of Denmark.
Is a revolutionary technology capable of mechanically converting organic waste into a biopulp that can be used for energy and fertilizer. This is to efficiently receive, process, and get rid of organic waste. First, mirrors across the weighbridge, where all accessible data about the waste are recorded and stored as documentation as required by law. The system is designed to be able to efficiently handle all types of mirrors. The delivered waste is either tipped into the receiving pit or directly into the receiving hall. The system and the technology are designed to be able to handle waste enclosed in all types of packaging. After this, the processing of packaged organic waste begins. Waste is loaded into a feed hopper by a front-end loader. In this system, the feed hopper is capable of operating for about 4 hours, but it adapted as required. Once the feed hopper is filled, the automatic process begins, in which the packaged organic waste is conveyed up into a small feed hopper by a screw conveyor. This process helps enhance the efficiency because the feed hopper fills the pulper very quickly. Pulper is a large rotating centrifuge which waste is mixed in water, quickly dissolving the mixture into a mash-like substance called biopulp. From here, the biopulp is sent to a separator, which separates the inorganic material from the organic material to send a more than 99.9% pure organic pulp to a storage tank and onto tankers destined for biogas plants. The plants extract the biogas from the biopulp as an eco-friendly, sustainable alternative to fossil fuels. The degassed residual product from the eco-ghee system is spread as biofertilizer on farmland, thereby contributing to the circular economy. Back at the facility, all the separated organic materials are sorted out. The dry materials are recycled wherever possible. The inorganic material left over can be sent to an incineration plant, which converts your waste of mine into district heating, benefiting all of us once more. Help us to be kind to our environment. It's simply common sense, and green at that.
Thank you. And that was all from my side.
Thank you, Lars. Thank you very much. The next presentation is by Dr. Simon Crook, the head of US Business Development at Nature Energy in the United States. He has worked in the clean and technology and renewable sector for 20 years now. And the last of those 20 years, the last 10 of those 20 years have been in the biogas sector. He has developed and managed biogas facilities on behalf of investors and owners. And these facilities have ranged from both small on-farm facilities to large standalone food waste facilities. Previously, he worked in a range of industries, including oil and gas and technology consulting. He also has a degree and PhD in chemical engineering. Simon, please go ahead.
Yeah, can you see the presentation okay and hear me okay?
Yeah, we can hear you and see the presentation.
Great. Yeah, I'm head of US Business Development for a company called Nature Energy. Actually, on the screen, you can see one of our biogas plants in Denmark. And I suppose in summary, what I'd like to say is that we've been, we believe, very successful in Europe, and we are now very active in the United States, looking for opportunities. And certainly, digesting food waste is something we're very interested in doing. So happy to speak to people who want to go on that journey with us. Why is it not going down? Ah, okay. So, we are within this sector a big company. We've got 300 employees and we aim to be 400 by the end of this year. Within Denmark, we have over a 30% market share, and we're the largest renewable natural gas producer in Europe. If Nature Energy were a country, it would rank third behind Germany and Sweden in terms of total biogas production. And as we extend outside of our home country of Denmark into the Netherlands and France and beyond, and into the US and Canada, we already have a pipeline of 40 projects that we're looking to deliver on. So as I said, we have 14 biogas plants, and actually we started producing biogas from a new plant to us in the Netherlands just this week. We also have a network of 20 compressed natural gas fueling stations, which can fuel up trucks and cars throughout Denmark. And our plants take a total of 4.4 million tons of organic waste a year and producing over 4.2 million tons of green fertilizer digestate. Between taking in the organic material and pushing out digestate, we also produce, in 2021, just over 6 million MMBTU, but actually that's already above 7 million MMBTU in 2022. And to put that in equivalent numbers, that would be enough gas to power 8,000 trucks. Our history of that is we actually came from being a gas utility in one part of Denmark, and we expanded to become we divested from that part of the business and then focused completely on being a biogas company. We acquired a EPC, an engineering business in 2018, and then have continued to grow since then. And the growth has been fast for a business like ours. I mean, it's been over 30% a year since 2017, and a lot of that growth has come very rapidly since 2018 with our new owners and a lot of new investment going in. And we've also seen that in financial results. So in 2021, our total turnover was over $250 million US. As I said, our home country is Denmark, and we have an extensive number of plants throughout Denmark. And actually, although I guess people who know nature know us for building large plants, a big part of what we do is actually a network. So we actually get the plants to work together to get so the sum of the parts is greater than the whole. Sorry, the sum of the whole is greater than the parts. This is one of our latest plants, Koskro in Denmark, and that is one of the largest RNG plants in the world. So it takes nearly 1 million tons of organic material into it. So how do we do it? Well, given the topic of today's presentation, it's certainly circular. So we, starting on the left, we collect organic waste. That material is processed depending on the type of material it is, whether it's slurry or manure or packaged food waste or unpackaged food waste. We put it into our plants, anaerobic digestion plants, where it produces gas, and then it produces a biofertilizer, as people have already talked about today, which can go back and help growing more food. We actually, our model is certainly very local. We use a co-digestion model so that we say, when we put a plant down, we look at all the material that's in a 20-mile radius and we say, is that enough to support a plant of the size that we wish to build? But also, what is the nature of that material? And we need to be able to take, a lot of the organic material in that area. So we work with farms, large and small, for example, although we don't always have to take manure. And in France, our plants aren't taking manure, they're just taking break crops. But also all the other organic type waste, so residues from food processing, waste food, whatever it be, we look to take that material from that radius. And as I say, these are big plants, so we're taking a lot of material. So we're taking, 0.5 to 1 million tons of material. So we would differentiate ourselves, I suppose. We would say that, we are a corporate RNG business. And what we mean by that is that we've brought both economies of scale. So our plants are large, and that obviously means that the plants can support a relatively large staff of around 10, and economies of scale in terms of production costs, which are important in a world of continued competition. But also it brings network benefits. We don't just look to build one isolated plant. We look to put plants relatively close to one another so that they can actually work together and share feedstock and also other facilities such as storage. We have a standardized design so that based on actually units, that's not to say every plant is the same, but we look to have repeatable units within that so that we can reduce capital costs and reduce operating costs. We also, as I mentioned, have a co-digestion model. So that means we can take a range of biomass, and that means that we can take biomass from a particular area. It also means that it reduces risk. So if one particular type of biomass falls away a little bit, then another type of biomass can come in. But it also has a real mixture of local biomasses such as manure, but also high energy feedstocks that can come from further afield. And we again look to balance that across our network. Most of our route to market is actually putting the gas into the grid for use, onward use in heating and industrial and other processes. And also bringing the scale of that many staff is also we can actually have a headquarters that can add value. So we have a central engineering, central construction team, central R&D and business development. You know, we believe, as somebody else said, that the anaerobic digestion is a great way of recycling nutrients into a fertilizer. And of course, with rapidly rising fertilizer costs, you know, farmers are really seeing that benefit and are more and more interested in that. So, you know, we are in the fertilizer business. And of course, you know, it's not just a great fertilizer with higher nitrogen availability, good soil improver, but also it's cost effective. Increasingly, we believe that the gas that we produce also won't just go into the grid for onward use in heating homes or into cars, but also actually will be upgraded. So already we're producing compressed natural gas and liquefied natural gas that can be used in maritime applications. But we're also looking to upgrade the methane and combine it with the CO2 into a range of, as a chemical feedstock, for example, liquid fuels for jets or actual materials that can produce textiles, carbon fibers for bikes, etc. So what are we doing in North America? Well, we are very active in the States, looking for projects and developing our first projects here. So we have established offices in St. Paul, Minnesota, and also in Montreal in Quebec. And there will be over 20 staff by the end of next year, and they're already getting on for 10 staff in the US. We've got 18 projects that we're pursuing across both the US and Canada. And we will be looking to go into construction early next year on one of those projects. And we expect to be producing across the 10 projects a similar amount of gas as we do in Denmark. So we aim to be, within the next couple of years, as big in the US as we are in Denmark. And we actually are not just a member of the American Biogas Council, we're actually also now a board member. And I mean, our investment that we're making is around $5.5 billion across the whole of Nature Energy, and much of that will come from investment outside of Denmark. Thank you.
Monday.com WorkOS, you can create the exact tools you always wanted.
Thank you very much, Simon. Our next presentation will be held by Lindsay Tucker, account manager at Novozymes North America. Lindsay has spent her career focusing on water and waste, with previous experience in the industrial and municipal wastewater industry. She is passionate about using renewable sources to help meet climate initiatives and is part of the Novozymes team using biological solutions to help create a more sustainable future. Lindsay, the floor is yours.
Thanks, Simon. All right, good morning, y'all. So I'm going to talk to you today a little bit about how you can use enzymes to enhance food waste degradation and improve biogas production. So I want to start off by telling you a little bit about Novozymes and who we are. We're the largest industrial producer of enzymes and microbes in the world, and we're based in Denmark. We have over 6,200 employees, work in over 30 different industries, and have over 6,500 patents, resulting in over 700 different products. So I mentioned a lot of those different industries that we work in. We work in some that go direct to the consumer, that our products may actually be in products that are in your pantry or in your fridge right now. A lot of beer and wine is produced using enzymes. If you have any lactose-free milk, that frequently is made using enzymes. And a lot of commercial or easily found dish detergents and laundry detergents are made using enzymes to help make them more effective and more environmentally friendly. We also are very closely tied to the energy production industry, both ethanol and distilling, the paper industry. So it makes a lot of sense for us to be looking at biogas and anaerobic digestion as well. So I mentioned that we work with enzymes and microbes, and I want to tell you a little bit about how those kind of work with different ones, and we touched on a lot of those already. So helping to make cleaner clothes with less energy, so enabling cold wash, better nutrition with less food waste, greener fuel, and higher yields in agriculture. So if we're looking at how a process might change using enzymes versus just a traditional biogas production process. So if we're looking specifically at source separated organics or municipal solid waste, they would come into your various production technology units. Let me see if I can change and have a little pointer here. Sometimes I can successfully do that and sometimes I can't. So come into the various separation units, and you'd add water, and then you would get a liquid fraction coming out and a fiber fraction. This fiber fraction would frequently contain all of your inorganics, your plastics, your non-degradable components, and sometimes portions of that source separated organics or municipal solid waste that are really tough to break down. And then you would have your liquid fraction that goes up into your biogas. Well, let me see if I can get rid of my pointer there. When you add in enzymes, you're able to reduce that fiber fraction that's going to the incinerator or landfill and increase that liquid fraction and generate more biogas. The idea being that the enzymes are helping to break down those organics that are coming in and turn them into a liquid more easily and allowing you to use less water to make that slurry. So I've got a quick video here that shows that. So I think that video does a pretty good job of summing up a lot of the things that I'm going to tell you a little bit more about with enzymes. There we go. I was going to say we don't need to watch that again. So in the video, you saw pretty clearly that enzyme addition helps to reduce that viscosity of the substrates that are put in. Well, this graph right here shows you in more detail the exact amount that viscosity changes when you're starting at 20% total solids after that enzyme treatment. So you start with a viscosity greater than 2, and with less than 5 hours, it drops pretty significantly to a viscosity of 0.5. And if it's allowed to incubate for closer to 25 hours, you can see that viscosity drop even further. It's a pretty drastic change that occurs pretty rapidly. So this is showing just a little bit again. So after pre-incubation, but prior to enzyme addition, you can see how the impeller in there isn't able to fully mix the waste, and that it's not a really homogeneous slurry. And then if you look over on the right, after 7.5 hours of incubation with enzyme addition, the slurry is much more homogenized and is able to mix really freely and is incredibly flowable. So the impact of using enzymes, basically the application of enzymes leads to better organic separation. So if you're looking just at the percent of the reject that's left over, so these inorganics, ideally, that's what the reject is fully comprised of. But oftentimes there's some more difficult to solubilize material left in that reject fraction as well. So enzymes help to reduce that amount of reject left over. So if you're looking right at the beginning, initially right after the enzymes are added, 99% of that reject fraction is still remaining. But as that time increases, you start to see that reject fraction decrease. So when we're looking at this percentage here, it's the percentage of what's originally the reject fraction. So in a normal kind of separation, if you're seeing 100% of that reject, so say it's 25% of your total matter coming in, well, with enzymes, after a 20-hour incubation, you're able to reduce that 25% down to a quarter of that original amount. You're also able to change the total solids balance pretty significantly. So looking at both the liquid fraction and then that reject fraction, you're able to increase the liquid fraction pretty significantly, so able to more easily send a larger fraction to the digester. And as well, changing that COD balance or the chemical oxygen demand, or an easy way to kind of look at how much stuff or potential energy is available in the substrate that you're adding to the digester. So at the beginning, we're seeing most of that COD remaining in the reject. But as that time progresses, you're starting to see that balance shift where the COD is being solubilized and being turned into the liquid fraction. And that same is going in the volatile solids. So that's just another way of easily looking at the amount of kind of good energy available, sugars or fats that are in this. So starting at the beginning with initial enzyme addition, you're seeing more of that volatile solids remaining in the reject fraction. But as time progresses, that balance again starts to shift with more of that volatile solids being solubilized and moved into the liquid fraction. So one thing we do need to look at with enzymes is there's a couple different parameters that need to be balanced for you to see the optimal results. If you're kind of moving these around, you do have to realize that one of the others is going to have to give a little bit more. So if you're having to run at a lower temperature, you might need a longer retention time and maybe a lower pH for that hydrolysis to work as effectively. Or you might need to increase your enzyme dose. If you're having a shorter retention time, you might need to increase that temperature as well as decrease the pH for that to work as efficiently as you might want. So just kind of a final summary, enzyme addition yields visible results. You're able to see a reduced viscosity and improved separation of rejects, as well as seeing increased throughput, reduced hydraulic retention time, potentially reduced foaming incidents or floating layers, depending on the type of substrates you're treating, with an end goal of increased biogas yield. So, thank you.
Thank you very much, Lindsay. We have now around 15 minutes left for any questions that you might have from the audience, and you are type in to the chat function, use the chat function, or go ahead and ask questions on just dialing. I can already see that we already had some questions that were answered, and since it's asking more questions, maybe some of you would something. Let's see, we have no more questions, right? Yeah. I maybe for you, Cloud, because for instance, we can see that, as you also mentioned, there is a big difference between Denmark and the United States. Denmark is a very small country. There are some conditional frameworks that are very different in the two different countries. And we were talking about maybe how to adapt this into the American or North American market. How do you see the potential, the market potential for adapting this kind of technology and using the Danish model into the American one?
I think there's a huge untapped potential in the US. Everything is bigger in the US compared to Denmark. So I think our approach with large-scale industrial professional run AD plants would fit well and fits well. I think one of the when we meet stakeholders from the Netherlands, from Spain, from some of the other countries besides the US where we work, is that again we need to valorize and we need to put a value on each of the benefits that biogas and the opportunities that biogas provides, which also includes the diet estate. As mentioned before, and that was also one of the questions in the chat, was the use of, for instance, the CO2 from the upgrading plant for food grade. So I think we need to recognize and share the experience from the different countries on, for instance, the safe use of food waste derived diet estate. But it's not easy. Sometimes I think it would be easier to be in the wind industry because there's not that many stakeholders in that industry, and it's not involving a lot of different value chains and cultures and for instance how farmers work. But just to answer your question, there is a huge potential, and it's great to see that the partnerships are being built between Denmark and the US.
Definitely. Thank you very much, Klaus. We also have a question. So if there are any, what are the different types of incentives from governments in North America and Europe for biogas plant operators and involving farmers as stakeholders? Do any one of our experts know anything on this and who can provide us with some valuable knowledge? I think, yeah. I think this question is more for
I would. Oh, sorry.
Yes,
I can see Klaus has a hand also. Is it okay, Klaus?
Yeah, Morten, just
well, I think there's one very important aspect. I don't think it's been addressed really in this webinar very clearly. Is there is a generic incentive for basically all farmers to be a part of this. I think, Klaus, you mentioned it vaguely. But that there is a considerably better fertilizer from the digested than the manure and slurry that you have before the digestion. Actually, when you look back 20-25 years, that was a key part of the driver for many of the farmers to start the facilities in the first place here in Denmark. Many of them were farmer-owned, farmer-run. And one big driver was the fact that they could in fact utilize the nutrients in a much better way. It's to give a number, it's somewhere between 10 and 30% better in terms of yield. I think the question was also about government incentives. I don't think there are explicit government incentives towards farmers being a part of the ownership of the facilities, but there is an incentive in the sense of there's an increased focus on the fact that we want to digest and we need to digest the digested or the manure and slurry. No one has imposed any regulation that it has to be digested yet, but it's definitely something that could be considered, at least to some extent. And then, of course, there is the incentive of making money of these facilities.
But just to add to that, back let's say 15 years ago, and that still counts in Denmark, is that since we have a cap on how many livestock you're allowed to have on a specific farm compared to the area there where you can apply the manure, due to the easier uptake for plants of digestate compared to non-degas manure. A Danish farmer could choose basically to buy more land or buy a biogas plant, or make arrangements with neighbors. So again, if you want to increase the production of the livestock, that biogas was also one of the options they had, and that still counts. So again, this is we're targeting what takes place on farm level and also what takes place at EPA and yeah, those areas outside what we're talking about energy.
Thank you very much for elaborating on that question. As far as I can see, we do not have any more questions. So I would like to say thank you very much to New York Circular City Week for making this webinar an opportunity, and a special thanks to our experts who have provided us with valuable knowledge on how Denmark has done, but also on how the specific technologies work. I have provided my email in the chat, and you are more than welcome if you would like any of our publications that we have made with Biogas Go Global with the Danish experiences. Feel free to reach out and we'll send them to you. And yeah, we also have the recording of this webinar and a presentation that can be sent to you. So thank you very much for today, and have a great rest of your day.
Take care, everyone.